This video will deal with our second problem type, which is a problem type called calorimetry. And our goal is to use the first law of thermodynamics to perform calorimetry experiments and calculations. This video will actually include information on how to do the lab, which will be on Wednesday this week. So when we talk about calorimetry, it's all the concept of heat transfer. We've already introduced the equation Q equals mT delta T, which is a way to calculate how much energy was gained or lost as temperature changed. There's also a demonstration done in class where 50 grams of hot zinc was mixed with 50 grams of cold water. And in that example, these questions have to do with that specific demo. The sample that gained energy was the water. The zinc lost the energy. And both our substances ended up at the same temperature. And that's because at thermodynamic equilibrium, which is what we established, temperature is always equal. What we can say about energy gained and lost by these two substances is that because they were in a system with just each other, whenever one loses, must be gained by the other. Because energy is never created or destroyed, it's just transferred. So as zinc cools down, the water heats up. Every single joule of energy zinc gives up, water takes in. That leads us to our first law of thermodynamics, which is that whatever energy is lost by something must be gained by something else. Okay? Whatever gained energy had to get it from somewhere. If you look back at some of the calculations we have been doing, we've been able to calculate energy given off or energy taken on by Q equals mc delta T. But what this first law does is rounds out our picture. Okay? If you calculate energy is lost, that means you could do a second calculation with that same amount of energy being gained. And vice versa. If you find out that some amount of energy is gained, you could do the exact same calculation on something that must be losing that energy. What this does is gives us our second relationship. Okay? If you can solve for a Q, that means there is a negative Q that also exists. Okay, if something gains 10 joules, that means something else lost 10 joules. Hidden behind Q here is mc delta T. So while this equation looks like it's two variables, Q equals negative Q, in all honesty, it's actually 8 variables. mc delta T for one substance that is gaining energy, and mc delta T for one substance that is losing energy. How we measure this equation is through a process called calorimetry. Okay? A calorimeter is an insulated device that will allow for an energy transfer to be contained so that you can make sure that Q equals negative Q. You're not losing energy to some other surroundings that you can't measure. Okay? And a calorimeter or calorimetry is a way to quantitatively, so actually come up with numbers to measure the heat change in a chemical or physical process, and specifically a heat change that includes a temperature change. Okay? So what we're doing here is we're measuring energy given off by a substance by measuring the surroundings. So if you can figure out how much energy the surroundings take in, you know how much energy the substance gave off. For example, we'll go back to food chemistry. If you want to know how much energy is released when you combust Cheetos, for example, you can combust a Cheeto, but then you need some way to actually collect and quantify that amount of energy. And one way to do that is through calorimetry. If you can have water take in all of the energy of the Cheeto that has burned, and you can quantify the amount of energy that water took in based on a temperature change, you then know the amount of joules that the Cheeto gave off, and you can change that to calories and to kilocalories, into food calories, and that's one way to quantify it. So a calorimeter is really a device that we use to quantify energy in a situation where it might be challenging. Some applications of when to use it, I've already said food burning, also a chemical reaction. Okay, if a chemical reaction produces energy, if you do that chemical reaction in water, whatever energy the water takes in is the amount of energy the reaction gave off. So you can actually quantify the energy of a reaction that way. And then just to simply find an energy change due to temperature change. And that's really what we're going to be doing in lab. So for the remainder of the video, I'm just going to focus on 2 problems, both of which will help you with the math you have to do tomorrow for the lab. Okay, one problem will be where we use Q equals negative Q to calculate the specific heat, and then one where we use Q equals negative Q to calculate for final temperature. So if you take a look at the problem on the screen, you can tell this is a Q equals negative Q problem because you have information about both metal and water. We don't have just one set of information, we have two sets of information. So I set up my problems like this, identifying both the X and the water in terms of the M, C, Ti, and Tf, and the MC, Ti, and Tf for both sides. And then you just fill in the appropriate quantities, making sure to keep the variables grouped correctly. So if you take a look at all the variables once they're plugged in, you can see you have everything for water to solve for Q, and you don't have quite enough information for your unknown to solve for Q. So you think of Q equals negative Q, there's two ways you could potentially do this. So one way you could do this is actually to set up one equation where negative MC delta T equals positive MC delta T. That algebraically is a little more challenging. The other thing you could do is just solve for Q of water, and then know that if you can calculate Q for water, then the opposite Q will be the Q for your unknown, and then you can solve for C. So you do it in two different steps. I'm going to show doing it in two different steps. So I'm going to solve for Q of water first. Q then equals 1954.15 joules. Don't sig fig this because you're not done. Okay? If this is a positive Q, then this is a negative Q. So for your unknown, negative 1954.15 joules equals the mass of your unknown times the C that you don't know times the final minus the initial temperatures. So if you do this to solve for your unknown X, you'll find then that X equals 0.450 joules per grams degrees Celsius. If you then look at your thermochemical reference table, you'll find this is the specific heat for iron. So your final answer is iron. So that's one way to solve a Q equals negative Q problem, is to get a Q and then make it the opposite one for your other, and then solve for your unknown. The second problem you'll have to do in the lab on Wednesday is to find the final temp of a system. If you look at this one, there's a lot less information given to you on the last one. And the hardest thing about this one is you can't solve for Q. You do have to actually solve into that one system of equations to solve for your unknown temperature final. So you look at your setup of variables this time, you see the problem is you don't know temperature final on either side. So you can't solve for Q of one side and then assume it's a negative Q of the other side. You've got to solve for TF. Now the nice thing about TF is, while it looks like two variables, it's only one, because temperature final is the same for both sides. So you can plug this into negative MC delta T equals positive MC delta T. In terms of figuring out which one should be negative, if you do the algebra right, it shouldn't affect your answer, but whatever one's hotter is the one that will give off energy. So you can make aluminum your hotter side and water your cooler side, and then solve for your TF. So that's the setup using MC delta T equals MC delta T. The way I like to solve these problems then is to multiply these two quantities together, and then whenever you get there, distribute that into the parenthesis, multiply these two numbers together, get that, distribute that into the parenthesis, then group like terms and solve. So I'm going to show you an intermediate step that I'll never look for on the test, but this is just to make sure you get the problem right. So there's your intermediate step. After I've distributed into the parentheses, those are my four numbers that come out. Now I group TF on one side and my non-TF on the other, divide the TF by itself, and you should get a temperature final for this problem of 36.5 degrees Celsius. From this, you should be able to do Form 1, which is problems actually from worksheet number 1. We also have homework out there tonight for doing the pre-lab. Email me if you have any questions. Have a nice night.